So, of course, that's planet Earth, but it's a space simulator. What are we gonna do with this? Let's go ahead. Let's go to the sun. Sol, I think, is what it comes up as. All right. So there's our sun. So you can see the sun, Sol. Oh, I suppose that's why it didn't happen to come up. Comes up with 13 planets. I don't know where the other ones came from. Should probably look into that. So, of course, we select the sun here. We have the distance. I think that's the distance. Well, that's the distance that I'm away from it. So I can traveling near light speed here. So in order to actually approach the sun here. So let's go ahead and let's zoom in here. So rotational period. We want diameter. So there's the diameter of the sun in kilometers. So really, really big. Alright, so landed on the face of the sun. It doesn't look like there's much there. So now let's go ahead and look for the Earth. The Earth is right there. That's humbling. But it's not humbling quite yet. So takes roughly about 8 minutes to travel for light to travel from the moon or from the sun to the Earth. That's in light speed. So, which is rather nothing. I mean, in the galactic scheme of things, that's nothing. But let's go ahead and we're gonna kick up the volume of this. So the one thing to understand is, so I can set this to 1C. Now, there is certain measurements that I'd like to point out here at this point too. So, the first conversion basically being miles per second to kilometers per second. So, just a standard conversions, just how Americans do things. So, kilometers per second to C. C is light speed, so 1C is equal to 299,792.458 kilometers per second. So, yeah, that's pretty fast. Apparently, of course, and I don't necessarily believe this, but that is the speed limit. I think there are things that can exceed that limit. That's yet to be seen. So then you have 1 AU per second is approximately 500.346 C per second. So that's a calculation that I did myself after poking around on the internet for a bit. So, probably have to take that with a grain of salt. I'm not really good with math. So now we go to parsecs. 1 parsec is equal to 3.26 light years. So we're not even getting to the largest ones yet. This is a large figure, don't get me wrong. But then we have megaparsecs. That's 1,000,000 parsecs. That's huge, but then we have a gigaparsec. That's 1 billion parsecs. That's ridiculous. Now, I'll keep that up here because otherwise this might get a little bit boring here. So I'm at 1C right now. I'm going to go back to my game. Oh, no. Let's select the Earth again. Okay, so we have planet Earth selected. So I guess you can see I'm a little bit less than 1 AU. So the AU is basically the distance between the Earth and at the Sun at a certain point. I don't remember the exact certain point. Let me look up Wikipedia for that. Let's bring it up here. Let's just make sure that we get our facts straight. Oop. Wrong article. Alright. So, astronomical unit is a unit of length now defined as exactly 149,579,870,700 meters about 93 million miles. So 93 million miles is the distance between the Earth and the Sun. Essentially observe the length of the semi-major axis of the Earth's elliptical orbit around the Sun. So, there you go. So, of course, this is a little bit closer to the planet. This is looking like it's a little bit more so towards summer, and that's why we're at 0.980 AU. So, you can see down in the bottom left-hand corner that I'm at currently light speed. So, I can kick this up to 1 AU a second, and I just press the button and I'd be there. What? That's not fun. It's kind of fun, actually. But, now, here's a major test here. So, right now, I'm going at the speed of light. Now, again, this is fairly humbling. This should take about 8 minutes in order for me to travel this distance. That's rather insane to think about. Something that you're going at about 299,972.458 kilometers per second. And this is taking 8 minutes to get there. That's a very long distance away. That's huge. You gotta think that it takes so long in order to get across the universe at light speed in order to get through. So, of course, with that in mind, I also looked up last night more information about light speed and everything too, not light speed, but warp speed actually. So like shows like Star Trek and everything. I actually found the strangest thing. I found an Angel Fire site that showed me what the it showed me what the conversions are for light speed, or what they believe is, anyways. So the basically it's considered like a multitude of warp. So warp 1 is light speed, warp 2 is 8 times the speed of warp 1, warp 3 is 27 times the speed. So if you put it up to 27 times the speed of light, it takes, this is nothing. This trip is nothing. It's like basically a few seconds. But as you can see, the distance, we're slowly closing the gap here. We're at 7.5 AU about. So we're getting there. It's just, geez, it takes so long. One funny thing too about this is that semi-major axis is 1 AU, of course, and the orbital period is 1 year. So basically all of our units of measurement, so 1 AU is the semi-major axis. So that's rather crazy to think about, that, you know, we're kind of a vain race. Of course, nobody can disagree with that. But, I mean, we have to make units of measurement just based off of where we are currently in the universe. We can't necessarily just, you know, not have this unit of measurement be something relating to that. So, still approaching Earth. It's taking so long. So we're at 6.3 AU. Still going. I'm gonna go ahead and switch a window over here. Go back. Oh no, I selected the wrong one. Okay, now we'll go back. Okay. So, you know, I had to switch it to a different window here, but whatever. You get the loss of time is nothing. So we're still going in, and kind of center this in here too. We're still approaching Earth, and at this particular point you should be thinking, wow, this is crazy. I'll go ahead and stop and turn around and see where the sun is. Should be able to find the sun about right there. There we are. So that's the sun. So still a rather large object in the sky, but we have traveled probably, what, 4 minutes or so, probably not that, probably about 3 minutes, to get this far. That's stupid. And there's our planet Earth, where everyone was ever born, ever will be born, probably. Never be able to get off this planet in time. We'll just end up being wiped out by something. No, that's probably not the case. We'll see what happens, of course. So, I'm still going. I'm almost halfway there. And this is light speed. This is the fastest that anyone can go according to the laws of physics. That's just messed up. So, and there's a couple other cool things in here that I would like to record as well before I end up ending the video here too. I'm going to travel the full distance here, but while I'm doing that, talking a little bit about this, I found black holes yesterday, and it's fairly easy to do to find black holes. We just basically search for the objects with the highest mass. So the cool thing about that, though, too, is that you get to see what exactly it is. This program does a really good job of showing you how to, or showing how light bends when light bends due to gravity. The theory of relativity. It's rather crazy, and it's rather cool looking too. I'll definitely do that after I get to Earth here. Other than that, though, too, there's a ton of different stuff. I went to Reddit. There's go to r/space engine. There's a number of posts there with what people have found out there in the galaxy. Some of it's crazy. Some of it's on the opposite end of the galaxy, where I'm just thinking, how in the fuck did you find that? So, I mean, there's no other way to put that. It's just, how in the world did you happen to find that particular object? And it was crazy because, and I don't know if this is something that's actually possible, because as I hear, as soon as an object gets so large, it becomes, and starts to look more spherical than anything. But there was a sun, and the sun was just kind of globular. It was just kind of blurbs. And there was this planet that was just basically right there on that sun. It was not far away from it at all. It was ridiculous. But, as you can see, Earth's getting a little bit larger here. We're still a little ways out, so 0.236 AU. We're getting there, and you can see that the object's starting to get a little bit larger there. But it's still a ways away. So, just keep going here. And of course, at this point, you're just watching this saying, holy crap. This is what it takes for us to get life-sustaining light. And not to mention, too, I mean, our planet's basically perfectly within the Goldilocks zone. So this is the distance of the Goldilocks zone. It's, in reality, it's nothing. There's very, very, very few planets that'll actually reach this, but that's still going to be in the tens of trillions. I don't even know if trillions is the appropriate word for this. And I mean, the reason for that being is that I could do a search right now, I could find hundreds of millions of stars just right off the top, right there. Okay, now we could start to see the object moving. If I end up moving like this, you can see that it's moving away, so I gotta be a little bit careful. So, we're still going. Approaching the target. I believe that might... No, that's not. That might be the moon. Yep, so that's the moon right there. That's Earth. Kind of looks like a star right from here, and you can see that it's starting to become a little bit brighter here too. Okay, so I'm gonna slow it down a bit, because that's approximately, well, we'll go back up here. Okay, so we're approaching it really, really, really fast. And we're here. Whoa! And we actually landed on the planet. So, that's the trip. That's the sun. Really hard to select when there's other objects right there anyways. So, that's the trip between the Earth and the sun. That's how long it takes for light to get from there to there. This program does an amazing job of that. Alright, so I'm gonna zoom out here.